This lesson is on linear inequalities. Let's consider the inequality given here. X plus y is greater than or equal to 3. What this tells us is we want to somehow represent on this graph all the points that when added together of their x and y components, the result is greater than or equal to 3. Well, first of all, we can think of all the ways we can add two numbers to get to 3, to make it equal to 3. So that's forming the boundary. Well, some of those points include 1, 2 for x, y, or 2, 1, or 3, 0, or 0, 3, or 5, negative 2. So we can plot those points. All of those points work, don't they? So 1, 2, 2, 1, 3, 0, 0, 3, 5, negative 2. You can imagine all of these points along this line are going to equal 3. But the question now is, what are the points that are going to make it greater than or equal to 3? Is 1, 1 going to work? Well, 1, 1 is 1 plus 1, which is 2, and that doesn't work. What about 2, 2? 2, 2 is 4. Yes, it's greater than or equal to 3. So this point works. 3 plus 2 is 5. That point works. 4 plus 2. So anything bigger than 1 plus 2 is going to give us something bigger than 3. And similarly goes for all these other points on this side of the boundary. So you'll soon realize that all you need to do with these questions is first find the boundary, the equal sign, and then decide which side do I shade. And in this case, it'll be everything on this line and outside of it in this direction. So, to graph a linear inequality, you first want to graph the line equation by pretending it's an equal sign. Then you want to choose a boundary type. So if it's less than or equal to or greater than or equal to, it's a solid line because it includes all the points on the line. But if you have an equation or inequality that's less than or greater than, then it's going to be signified by a dotted line because it's not all the none of the points on the boundary are included, but all the points outside of the boundary and just up to it are included. It's kind of like a border, right? So the Sumas-Abbotsford border, you are in the middle of it, and you're not actually in any country until you cross the border. Finally, you need to determine which side to shade. So you can test a point somewhere, and that basically tells you that the rest of that side is going to work if that point works. So let's apply this process. First, we want to graph the line. So we're treating it as if this was 3x minus 4y equals 12. And recall the easiest ways to solve it for the slope-intercept form. So subtract 3x, and you get 4y equals negative 3x plus 12. Divide everything by negative 4, and you get y equals 3/4 x minus 3. So that means we start at negative 3 and go up 3 over 4. Up 3 over 4, and so on. And that forms our boundary. And this boundary, you have to decide, before you draw the line, decide, is it dotted or solid? Well, in this case, we're not including the boundary because there's no equal sign. So we need to make this line a dotted line. So it's representing the boundary, but none of the points on this line actually satisfy the inequality. So now let's test a point a nice point to test is usually 0, 0, unless, of course, the line goes through it, then you can't use that point. So let's test 0, 0. So if we test 0, 0, that'll be 3 times 0 minus 4 times 0. Is that less than 12 is the question. Well, is 0 less than 12? Yes, it is. So that implies that everything else on this side of the line will work. Nothing on this side will work, so don't shade any of that. And here you've basically represented all the points that make that graph work. Let's try x less than or equal to 2. So again, the line would be x equals 2, which we know is a vertical line, like so. But what kind of line do we draw? Well, the border is equal to, so we want to include the line. So it's a solid line. Now we have to decide which side we shade. Well, in this case, we want everything to have points that are less than or equal to 2. So in this case, we want all this stuff here shaded. Notice, pick a point, that point there, which is -9, -3. Well, is the x value less than or equal to 2? -9 is less than or equal to 2, so yes, it is. Another one here is a little more complicated, so let's find the line first. So we got to simplify this. 3x plus 3y plus x less than 6. Get everything together, and we're actually just going to pretend it's an equation for now. And so we've got 3y plus 4x equals 6. Get y by itself. -4x plus 6. Divide everything by 3. You get y equals -4/3 x plus 2. And we're going to use a dotted line here because the boundary is not included. So you start at 2, and then you're going down 4 over 3. Down 4 over 3 because of the slope. Or you can see it as 4 over -3, which is up 4, left 3, up 4, left 3. And it's a dotted line. Now we just have to decide which side to shade. So pick a point, say 0, 0, plug in zeros, so test 0, 0. So you'll have 3 times 0 plus 0 plus 0. And the question is it less than 6? So is 0 less than 6? Yes, it is. So this side is shaded. If it wasn't, then you would shade the other side. Let's look at an application problem here. Robert has up to $8,000 to invest in 2 companies. Robotronics sell for 40 each. Macrocorp sell for 50 each. Graph all his possible investment possibilities. So let's have one, say, Robotronics on the x-axis and our Macrocorp stocks on the y-axis. So Robotronic is our x, Macrocorp's our y. So essentially, every x is multiplied by 40 to get a $1 possibility, and every y is multiplied by 50 because each of those are sold for $50. And we can only spend up to $8,000, so it has to be less than $8,000. Now, specifically, they didn't say up to and including, but this actually implies in English that it's all the way up to $8,000. He doesn't want to spend any more, so we're going to call that equivalent as well. So now we can solve this and graph it. So let's solve it for y, pretend it's a line equation, and find the boundary. Where is it equal to 8,000? Well, it's equal to 8,000 if we shift this over. We get 50y is equal to -40x plus 8,000. And we divide everything by 50. So that gives us y equals negative 4/5 x plus 160. Great. So this is going to help us, but the scale's a little funny. So let's try and work with it. I think we should go by tens. So 10, 20, 30, 40, 50, 60, and so on, up to 160, which I believe is right here. It came off the graph by 1. That's all right. If I had graph paper, I could extend it a bit. Now let's keep the scale the same for this side as well, just so we see it a little clearer. And we're going down by 4 and over by 5. So remember, you can actually expand this so that it is still down by 40 over by 50. It's easier to work with on this scale. So if we go down 40, that's actually going down 4 of these steps to 120, 140, 130, 120 is right here. And then over by 50, which is right here. So that's our first step. And then we keep going. So down 4 over 5. Down 4 over 5. And eventually it gets to over here. You could count and figure out how much that is. Now, notice because it's an applications problem, you don't want to keep going past this. So because he only has up to 8,000, you can tell that this will be less than or equal to, which will be smaller than. But notice I'm not shading anything with the negatives because he's obviously not going to buy negative 10 stocks. So this represents all the possibilities of combinations of stocks he could buy if he only wanted to spend $8,000.